Hello, my name is Thoran Evans, and I'd like to share with you briefly a topic I found unique and fascinating called phonotactic probability. As someone with a side interest in learning languages, I think this really combines statistic and language learning in a unique and interesting way. So what is phonotactic probability? Well, we all know that human languages can be vastly different and can have vastly different sounds that are common to that language. To show you what I mean, take the image you see here on the right. Tres tristes tigres tragaban trigo en un trigal, or in English, three sad tigers ate wheat in a wheat field. Notice how much the sound tr comes up in this short Spanish sentence. So if we were talking phonotactic probability, we might say that the tr cluster has a higher phonotactic probability in Spanish than it does if it were in English. Now this same idea can be applied to any spoken or written language, and this is what phonotactic probability studies. So of course, it takes more than just noticing sounds in a language to find phonotactic probabilities. We do have to do some sort of math with them. And the two most common types of phonotactic probability are unigram and bigram averages. To illustrate this better, take a look at a random non-word like blip. In a unigram average, there are 4 phoneme positions considered: bull, bull, nk. A unigram average would look at words in the body of work, which could be an entire language, a book, a play, a speech, really anything written or spoken. And with that phoneme position and related to how many of those words have that specific sound there. So for example, click has the same number of phoneme positions as blick, except there is a C in the first phoneme position instead of a B. Now a bigram works nearly the same exact way, except now in a bigram, blick is considered to have 3 phoneme positions: bull, l, and ick. So a bigram looks at clusters of 2 sounds instead of just one, which is the case of the unigram average. The actual formula to calculate phonotactic probabilities looks really big and scary, but I think it's helpful to consider our old friend, the Bayes theorem. In Bayes' theorem, an event A, right over here, is subdivided across some other events. And then what Bayes' theorem does is compute the ratio of a specific section of this event A to all other events that also coincide with the said event A. And although the analogy is not perfect, the idea of comparing a smaller event to a larger one that encompasses it comes into play here. Each term calculates the phonotactic probability of one phoneme position by taking in the numerator the sum of the log frequencies of words with the specific cluster in a specific place. And then it divides it by the sum of the log frequencies of words that just have that phoneme position present. So for example, in the bottom is sort of like the larger overlapping event A. And bull being in the first position might be termed as an event A and B1, where B1 is the event where bull is in that phoneme position. The same is done for all other phoneme positions, and the individual terms are all added up. Then we divide by the number of phoneme positions that the word has. This specific equation is for a bigram average, and in this case, blick has 3 phoneme positions. So we would divide our sum here by 3 to get our final phonotactic probability for the word blick. So I know what you guys might be asking. Why would this be important to a stats or mathy type major? Well, phonotactic probability can help us understand the difficulties of second language acquisition. Going back to Spanish, a common sound that exists in Spanish and doesn't in English is the double R roll, rrr. For English native speakers, this sound can be incredibly difficult to make at first, simply because it's not a sound that typically appears in English. So you might say that in English, its phonotactic probability would be probably around 0. While in the Spanish language, it would be much higher than that because it occurs much more frequently in that language. By using a probabilistic approach, we might quantify then the difficulty a person might have learning a language, and we could pinpoint on which phoneme clusters they particularly struggle on, and hopefully they can focus on those to improve their fluency. Some studies like that by Hahn et al. 2016 go even deeper and look at the effect that phonotactic probabilities and noise density could have on the listening comprehension of second language speakers. So that was a very bare bones description of what phonotactic probabilities are, and I hope this helped show you, the audience, a way to think even more creatively about how probability and statistics can be applied to the world. But I bet you didn't know that the very sounds you make with your mouth can actually be studied with probability. Thank you.